Okay, hello, welcome everyone. This is the Georgia chapter of American Statistical Association. I give a very brief history of what we are going to see. Our chapter, Atlanta chapter, started in 1961, and we traditionally have 1 or 2 meetings each year in varied locations, mostly in Atlanta, in Athens, though. And now, in 2006, Atlanta chapter renamed to Georgia chapter. And this year, we are starting this winter lecture series, and we are very honored to have Dr. Bin Wu to be the inaugural speaker. I request Professor Jeff Wu to give an introduction to the speaker. And before that, we also have a plaque to honor our token of appreciation to Dr. Yu. I will send it to you. I just got it delivered today. Professor Wu. Jeff, would you like to introduce?
Okay, I can start.
Yeah.
Well, it's my honor to introduce my very good friend, Professor Bin Yu. Bin has given us honor in the local ASA community by agreeing to give us this talk during the pandemic lockdown. In fact, I checked that she gave another distinguished lecture about 6 weeks ago at Georgia Tech. So apparently she's a local favorite. Bin is an international renowned scholar, so I don't think I need much introduction. I'll be very brief. She's a distinguished professor of a very long title, and joined between statistics and electrical EECS, and she has garnered many honors. I only mention the membership of the National Academy of Sciences, the IMS Reach Lecture, and she served as president of the IMS. And today, the title of her talk is a bit tongue-twisting, Veridical Data Science, and let's welcome Bin.
Thank you, Jeff.
Thank you.
It's an honor to be introduced by Jeff. I'm very pleased to be here, and especially to have 2 of the people I looked up to, still do. One was a young statistician. I think when I first interviewed for a job at Wisconsin, Jeff was there. By the time I arrived, he left. So, and actually Lynn organized one of the early workshops on new researchers. At the time it called Pathway to the Future. I think one was a fresh PhD. So I'm very glad to see both Jeff and Lynn at my talk. So hope I have honest comments from them. So Jeff already said this word is a little like a tongue twister. Many of you probably don't know the meaning, which I actually didn't either. When Tianjin from Columbia actually suggested the name for my paper, used to be called 3 Principles of Data Science. And veridical means coinciding with reality. And we're kind of in the age of AI. And I like this quote from Bill Gates. AI is like nuclear engine energy, both promising and dangerous. And here on the right, you have a list of things that AI is impacting our lives. Of course, under the hood, AI, a big part of AI, the engine is actually data science or statistics and machine learning. And Conway's one diagram says that there's 3 areas: domain knowledge, computer science, and statistics, and the intersection of that is the very popular area called machine learning. Actually, the name of data science had a lot to do with Jeff, who was the first actually put forward this term in a 1985 talk he gave at the Chinese Academy of Sciences. And for me, the goal of data science is really to solve real problems. And I believe solving real world problems have to be the mission, the anchor, and the goal of data science. I had a discussion on 10 challenges of two sets of papers, one from Xuming He and Xihong Lin, the other from Jeanette Wing from the CS point of view. The first set of authors wrote about the statistical point of view. So I believe methodologies, algorithms, approaches, and theories have to be at their service and appraised relative to how well they help solve them. I have been engaged on my group for the last 10, 15 years in mostly biomedical problems, neuroscience, genomics. And we had this news about AlphaFold on protein folding recently, and electronic health record and precision medicine. So the example I'll get to of the project, it's from precision medicine to look at a particular drug called Vioxx. Vioxx was a very famous painkiller, was approved by FDA in 1999 and was pulled off market by Merck 5 years later. So if you look at the data we'll analyze, try to find subgroups, we have to really think about the whole process, not just the modeling, and don't care about where the data come from. So I like to think we should think about data science lifecycle as a whole system, like engineering system. And we have these different parts, like domain question, data collection, data cleaning, all of these different parts, these little circles, have multiple choices we use human judgment calls to make. We usually choose which problem to work on, how to formulate the problem, and which package to use cleaning, or which graduate student asked to clean the data, and which models we use. We now have a huge arsenal of methods on how you're going to perturb the data, even for the IIT case. Do you do cross-validation, you do bootstrap, or you do subsampling? They're all related, but they're not exactly the same. Would you get the same conclusion? So every step, every circle will have multiple choices. I think what's missing is really a quality control and standardization of the process. Very much, what Jeff and many others work on about quality control was in my mind while thinking about this PCS process for data science. It's like a quality control process. And this just lists some specific questions that we have to consider. Which problem to work on, right? I end up working on this randomized trials data that David Madigan, co-senior author, has access to. And we had 2 studies, right? That was great, we have external study. And then we want to binaries the features. How do you make the cut? And what plots? And what we look at multiple metrics. And what data perturbation? And we have 17 different models, right? How do you consolidate, integrate the results? And plots you try to put in the paper. You do a lot more plots than you choose. And what's the takeaway conclusions? So all of this are things I think should be made transparent and documented. If we want veridical data science or truthful data science or trustworthy AI, we can either take a preventative approach, basically share best concepts and practices to maximize the promise, or the intervention approach, like risk management. So the talk will be concentrating on the first approach, which how can we share best practices and ideas and concepts so that we really have a quality control data science process. To be precise, veridical data science we define in the paper, which I'll introduce, is to extract reliable and reproducible information from data, but with an enriched technical language to communicate and evaluate empirical evidence in the context of human decision and domain knowledge. Statistics it's a storied and pretty historical field. But while we embrace new challenges, the concept need to involve new terminologies, new ideas have to be introduced. So that's what I mean by enriched technical language, instead of even criteria for evaluating statistical work. I just feel like asymptotic consistency, which served us well in the past, might not be the right metric in this big data era. If I work with data scientists, scientists, it's almost impossible these days to get everything. Usually we try to shrink down the possibility of experiments. And then we do a good job if we can do that. So we're never in the asymptotic with infinite signal to noise ratio. So I think the algorithms should be evaluated with a different kind of guarantees than asymptotic consistency. And the result of insisting on asymptotic consistency actually make us can only analyze very simple models, because that's where we can have this consistency. But in fact, we can be useful when we're useful. We don't have the consistency, but we're still very useful. So I think the theoretical criteria need to evolve to accommodate that. For the rest of the talk, I want to introduce the PCS framework for Veridical Data Science. So we designed the Veridical Data Science as a much bigger umbrella than the particular approach my group takes. I hope everybody at least will agree we need really reliable data science. And the second part will be a case study to analyze a clinical trial data called VIGOR and try to find subgroups that the drug actually works, not without the bad cardiovascular effects. So what's PCS? The paper appeared under the name of Veridical Data Science. In the beginning, I was giving talk called Three Principles of Data Science with my former student now at UCSF, Carl Kumbier. And it's built on these three principles. P is predictability, that made very big by machine learning. Of course, statistics we consider predictive, but it was not at the center, right? We did predictability, but when people think of statistics, they don't think about prediction. They think about p-value and things like that. And computability was put forefront by, again, machine learners. We always did the computation for a long time, but it was not the first consideration when we designed something. We had principles and we think about computation later. And stability is really expansion on statistical inference or sample-to-sample variability to the whole data science lifecycle. And my co-author of the book, Rebecca, has this nice drawing to show that you need all three components to make a Veridical data science train. So PCS really bridges Leo Breiman's two cultures and attempts at unifying, streamlining, and expanding on ideas and best practice from both machine learning and statistics. And PCS connects science and engineering. I think data science is really a field, both scientific field and engineering field. Predictability and stability embed two scientific principles, prediction and replication, and computability is necessary in terms of scalability, risk of convergence, more from computing theory, but also computability under PCS includes data-inspired simulations. That data often is not enough, even we have big data, because the problem we try to deal with are very complex. So we should augment our analysis design of algorithm with grounded data simulation that capture domain knowledge, and we can do actually many different versions of the same simulation to have robustness or stability in practice. I started embarking on this road of advocating for stability about 10 years ago. So this was actually a paper based on my Tukey lecture, 2012. At the time, I was working on lasso and realizing if you want to interpret lasso, you perturb the data. Well, I was working on neuroscience problem. The selected features would differ quite a bit. At the same time, I was trying to make a connection with Tukey's work on robust statistics. So I ended up putting them together, just called perturbations. So we want stability as a minimum requirement relative to data perturbations, which you justify not any perturbation, but reasonable ones, and also model perturbations, also reasonable ones that do good prediction, as a minimum requirement for interpretability, reproducibility, and later got into causal inference, also for scientific hypothesis generation or intervention design, I call scientific recommendation system. Also fully aware of robust statistics, and purpose didn't choose robust statistics because had a particular use. I want to be broader, and also in numerical analysis and dynamic system, there's a concept stability. So I thought that was broader, but it's really robustness in a very broad sense. If you think about this whole system as like hardware, and you try, predictability is reality check, saying that this system actually is useful. It captures reality. And then stability is like shaking the system so that the system doesn't fall apart. The shaking comes a lot from human judgment calls on each of the steps represented by the circles. And the PCS workflow, PCS framework has the workflow and also documentation. And the workflow basically try to integrate or incorporate the three principles in every step of data science lifecycle. So in problem formulation stage, what does P mean? P means you want to think about the future. You never do analysis without thinking about whatever develop will be useful in the future for another population, another situation. So it's never just about the data in hand or the problem in hand. And stability is there, right there. You have multidisciplinary team. Then the same English word might mean different things. I had experience talking to a cancer biology from Berkeley Lawrence Lab who developed a theory about cancer, basically treating cancer as an organism instead of just disorganized cells. And her theory now has been accepted, after 30 years. And she has something about the biological structure. She used the word matrix. And over dinner, I tried to tell her my matrix is different from her matrix. It just didn't quite go through. If I end up working with her, we better make sure that when she says matrix, it's not my matrix, so I'll find another word for one of the definitions. So linguistic stability is already there when we start talking about problem with multidisciplinary teams. We also expanded PCS inference to perturbation intervals into the confidence intervals. And if you have a well-justified probabilistic model, you basically go back to classical inference. But I want to be able to talk about perturbation at the cleaning stage, compare the Su model with random forest model. So things cross models and bring data from PDEs instead of just only stochastic. So all these forms, which we know under ID assumptions, but usually we only try one. If you try different forms, you might end up different result and you need to consolidate the result. And the PCS framework like to encompass also data modality choices, right? There's this famous labor kind of survey, international survey. They will go to different countries and interview people about their job skills. Sometimes use audio, sometimes use video. Do you get the same conclusion? Genomic data, proteomic data, did you get the same data or same conclusion? Also PDE, we can take PDE simulated data as one form of data, just put it on the same computing platform. It can serve as regularization. You basically pull your model toward this manifold generated by the PDEs. And data under different environments is also a form of stability and differential privacy. Now Census is going to use it. And the famous adversarial tags to deep learning algorithms. Not for medical imaging, also for biometrics images. I just was at a talk in Florida State over the weekend. And there was Aaron Ross was talking about how the deep learning can take two images and make kind of mixed image. And you can tune the parameters so that the image can be recognized as one of the people or none of the two peoples by the automatic recognition system. So that's a concern. That's also adversarial tags to the AI system. So depending on the situation, you might do different perturbations. Another example insight, I was just reading this morning about people now, the new economists seem to think that debt is not as bad as we think. So 10 years ago, two economists wrote a paper called Growth in a Time of Debt. So they made the conclusion that looking at different countries every year, every country's data, look at the public debt versus economic growth. And they made the conclusion that high debt GDP ratio is bad for growth. And this paper was cited to support austerity policies in UK and Europe. This morning, the opinion piece I read seems the economists are shifting their opinions about that. A few years later, 3 economists from Amherst tried to replicate the result. They realized that 3 data points from New Zealand somehow were missing from the first study. And there were some coding errors and unconventional weighting. After all this are rectified, the conclusion stopped to hold. So this was a very piece of important evidence that actually was not stable relative to this probably oversights in the data analysis. So any important conclusions probably should be replicated by independent group as a minimum, but we don't have that. And as I mentioned, Tukey had started robust statistics is really looking at model perturbation. You want to have some measure about the center of a distribution, which is robust to outliers, and that's why we probably do trim mean instead of doing the mean. And then we have lasso and ridge, both used a lot. And we have different modes in non-common optimization like deep learning. Luckily, a lot of them we find use gradient descent are pretty consistent predictions. But they're also funny that they're also kind of subject to the same adversarial attacks. So that's something we try to understand. I'm actually part of a group grant to Science Foundation and Simons to understand deep learning from a theoretical point of view. And sensitivity analysis, I would see it's a special kind of stability analysis from Bayesian modeling. And one thing is also researcher to researcher perturbation. We have now 71 people. If we're giving the same data, same access to domain knowledge, do we get the same conclusion? I don't think so. I think we're going to have many different, hopefully we agree on some things, but there can be a lot of things the teams will differ. In climate science, we already have 9 established models. If you predict global mean temperature change, it's from 1.5 to 5.5. Documentation is a big part of PCS. Here we have reality. I think models, before you establish connection with reality, just mental constructs. Not because we write down as X, there's reality. The correspondence with reality has to be established. Is there a bridge? Actually, don't see it. It's your job, our job, to put quantitative and qualitative narratives to make the connection through documentation, to record the judgment calls. Otherwise, we are not on a solid foundation for what we do. Many people ask me how to choose perturbations because you never finish your work if you try all possible perturbations. For the list I gave you, if each has only 2 choices, you have exponential, I have like 8 or 10, it just takes a long time. So you have to make choices and you document them. But at least I think we should try data cleaning, maybe doing twice by 2 graduate students. And we also maybe just fix other things, at least do marginal perturbations. That's what we'll do as well in the next, in the project I will present. If you pledge the stability principle, and if you do too many perturbations, you end up with nothing, because nothing will be consistent. Unlike the cherry picking model hacking, right? The more you try, the more seem to get more results. That's why if you go with stability principle, then they will encourage you to think hard. You only do reasonable perturbations and document them. There's no magic, right? I cannot tell you whether your perturbation is reasonable without knowing the context. But you document it will help me to judge and help yourself to think more clearly, and maybe help other people, the possible users of your result, can have oversight on what we do. And I think we'll all become just naturally more careful, more rigorous with oversight. Suppose we all now becomes just formally this year, all my projects in my group, we need a PCS documentation. Even before this, before the paper was published, we do some things were not consistent. Forming this framework really helped us, even in my group, to be more thorough and consistent than before. And the PCS inference, we added really a perturbation screening step. I have been pretty concerned while I was sitting in some qualified exam committees on campus from other departments, people just sometimes testing 2 horrible models. And they will choose one because Neyman Pearson allowed them to choose one, but they never check any of the model actually capture reality. So that's really the motivation. Before you do hypothesis testing to do inference, you should check the models pass predictability test. Otherwise, you should reject both instead of choose one of the lesser bad ones. And then you can also, in these perturbation intervals, incorporate the perturbation on the data cleaning and even different classic models. Suppose I want to rank important genes for a particular cancer. I can take lasso and I can take random forest. And both of them might give similar prediction performance. And then I have 2 rankings. So you need to consolidate the 2, maybe only take the genes which appear on top for both of them. So this perturbation idea allows you to do that. From probabilistic framework, I'm not saying that it's impossible, it is much harder to bridge from random forest to lasso. But under this framework, conceptually, it's pretty straightforward. And it's very easy to explain to people from outside this perturbation idea. because you don't, it's common sense. I even found quotes from Greek philosopher like Plato about how important stability is for knowledge generation. And then you have perturbation interval. Again, if you have a very validated probabilistic framework, you just do the perturbation like bootstrap, you go back to this traditional confidence interval. So this is really expansion on the traditional inference and being realistic about what we do. So before we do all kinds of cleaning, and then we do a probability model, and we never really report on the impact of the cleaning on the probability model. I just felt like I want to be more transparent and more faithful to what really happens in practice, and have that reported and be taken into account in the perturbation interval. We have a recent paper really implementing this PCA inference for epistasis discovery using biobank data, UK biobank data, and have a positive, relatively high signal positive control for red hair. But this is a part of the Causality BioHub project with cardiology from UCSF and Stanford. We really try to find genetic drivers of cardiovascular diseases, which we are now doing, but we did a proof of concept with something easier. Finding nonlinear epistasis, even for red hair, is actually quite at the frontier for human data. And I can say that actually the climate scientists already practicing PCS inference. They always have these plots of 9 models. We should start doing that, right? We don't, we cherry pick. I think we just be better for everyone. We just report what we do. And the PCS program try to give some railing for how, or standardization, how we do that. I think many good groups already doing that, but I think hope they keep consistency, more thorough stability analysis. So the second part, I want to share this project we just finished. So this paper appearing in the special issue in International Statistics Review to celebrate Brad Evans' winning of the International Statistics Prize last year. And the title is called Stable Discovery of Interpretable Subgroup Via Calibration in Causal Studies. So this is a project, David Madigan and I are the senior authors, and are really driven by 2 very bright, talented young scientists from my group. Raz, who is an EECS student, senior student, and Yan Shu, who is a postdoc. And also 2 junior members, Brayton and Mia. And we also have a physician scientist, David brought in Kevin to join the team. So it's a pretty big team and really worked really well together. So this is about the Vioxx. As I said, Vioxx was a very popular painkiller. 20 million people already use the drug. And you can find this NPR report 207 saying that Merck agrees to pay nearly $5 billion to settle lawsuits from consumers contending the painkiller Vioxx cause heart attacks and strokes. The safety problem Vioxx and the withdrawal Vioxx from the market was a watershed event in regulating prescription drug in the US. Vioxx is a so-called NSAID, non-steroidal anti-inflammatory drugs. It's known that to increase GI events, stomach problems, but compared with the other older drugs seem to be better. And it was approved by FDA 1999 and made the annual sale $2.5 billion. These drugs are very expensive. So the average cost of developing a drug ranges from $4 billion to $11 billion. So it's very expensive. And I couldn't find a precise price for the R&D for Vioxx. So this VIGOR study find that the Vioxx increased the risk of vascular events like strokes and heart attack. In particular, 1 man died after 1 month of take of Vioxx. And there were like 3,000 other people sued Merck for side effects, serious side effects. So 2004, Merck withdrew Vioxx from the market. And there was an FDA panel seemed to be indicating that they were receptive for new drug application with appropriate risk labels. And I did a little internet search. It seems some smaller company might be interested in doing the generic version and maybe need a new application. So right now, I think it's off the market. So we were set to do precision medicine. Can we find the subgroup patients who benefit from Vioxx, but do not suffer from its drawbacks? We want to use the PCS, find predictive, stable, and interpretable subgroups. And we got lucky that they had another study. We can kind of validate what we found. So this is about 8,000 patients carried out in 300 centers in 22 countries. The control arm is Vioxx. No, the control arm is naproxen, was older. It's non-selective painkiller. The reason Vioxx is kind of bad for heart problem, it seems to be altered some pathway that make the blood more likely to clot. And the patient was selected from arthritis patients. So this is not a random sample, but because this is the people who have pains and they need to use painkillers. So this is just some basic, this is a randomized trial and Neyman-Rubin framework with a superpopulation. But this, you have to justify why the data is like, but we really don't need that. We didn't prove any theorems, we just get data result and validated. And we have a randomized experiment. And the average treatment effect, that's what usually FDA is after, to show effectiveness through every treatment effect. And you always have two potential outcomes for one subject. You never observe both unless you have a washout period. And the conditional average treatment effect is condition on certain features and look at the average treatment effect for that subgroup. And this is a way towards heterogeneous effect treatment estimation. So the Vioxx GI outcome research, that's called VIGOR. The result in the table shows that the GI event for the control arm, the old drug, have about 3%. And the Vioxx group has a reduction 1.6, ATE is the difference, 1.6%. So it's better than the control arm, which is naproxen. And for vascular events, it's worse than naproxen because the rate increased from 0.4% to 0.6%. And that was the reason the trial, there was a withdrawal of the drug from the market. So our question was, can we find subgroups that we can mitigate the bad side effects? The problem is that if we decide to go through the CATE estimation, there are many, many, many choices. You will see that we end up comparing 17 different CATE models based on mental learning, machine learning, and I won't have time to get to including some from my group and collaborate called the X learner, and there's also T learner, there's also S learner, there's BART. You can mix lasso in the middle of it. So just many, many, many versions. And model validation is hard because unlike supervised learning, we don't have always a label, right? For every individual, you only have one of the two. You really want the difference. So you have to kind of group them to look at calibration. And the percentages are pretty rare for both events. So in a nutshell, our contribution is really extending the PCS framework from supervised learning. That's the paper mainly was about. The ideas are there, but we didn't really develop to causal studies. We introduced calibration-based predictive tracks, so the P. And then we did many stability analysis. At the feature engineering step, kind of data cleaning and modeling approaches. And we did 12 different data splits. And all of that, we seek some consolidation integration of the ideas. And we also end up doing interpretability search to find the groups that are interpretable, not just, oh, there's this, if you cut the prediction of CATE and then whatever fall down beyond a certain number, that's a very irregular shape. We didn't want that. And that's helpful to extrapolate to an external study. And the binary features we had are some like gender. We also make country, we have 22 countries into US versus non-US, so we binarized. And we also have age cutoff. We look at two thresholds, 60 or 65. And we did quite a bit perturbations to make sure our conclusions are robust. So we turned everything into a binary feature. And the data split, we set aside the test set we never touched. And with the training, we have a validation fold. And for the 3 training folds, we also permute that many times to end up with 13. Okay, so for each validation fold, we change the training fold. This is, again, a judgment call, right? You cannot avoid some judgment calls in the process. We hope we remove some of the arbitrariness, but you cannot remove completely. If you look at one particular CATE, is from X learner with random forest. We need 2 base learners, and we have a cross learner with lasso. So the idea X learner is that for 2 groups, you just use the random forest to do the prediction and the treatment and to predict the outcome, right? Because you have outcome, which is a GI event. So for treatment group, you fit one. For the control group, you fit another one for the outcome. It's a binary classification problem. And when you put them together, you use the difference, you fit the lasso. So that's what it calls learner. So it's really building on, it's a mental learner, building on machine learning. And you cut this particular CATE estimate, this is all training data, that vertically and look at the top, and then you can see that the blue curve down there is the model CATE. That means it's predicted from the model. And the Neyman CATE means you just take this subgroup and look at the average ATE for this subgroup. That's what they call Neyman CATE. And they're pretty much aligned. And for the validation fold, you can see there's some discrepancy. And we have 17 of them, right? So in a nutshell, the CATE model do not really generalize. These groups don't generalize. But for each CATE, the bottom group seem to be pretty stable. So the bottom group really says that for this bottom group, the improvement over naproxen is now minus 0.6%. It's like 5%. So it's much better. Sometimes you might even trade that off. You can really help the GI event. Maybe the risk for the heart disease might be more tolerable, right? So that's what you can say. This is the benefit is so much bigger. But subgroups are different, right? You have 17 different surfaces. You cut vertically, whatever map down to the feature, it's just different shapes and different subgroups. So we need to consolidate that. And we also need to know which of the 17 models we should use to consolidate. And in the end, we developed something like a T-statistic to measure how much improvement a particular method is from different perturbations. And for different, we don't know how to cut, you should cut into 5, so we did different from the lower end, bigger and bigger. So we did many, many different possible choices and aggregate them into this model, this ranking through this T-statistic. So classical statistics is still useful because T is more comparable across different perturbations and different methods. We have 17 different models, and we have this different perturbation, we have different ranking. And what we did is that we look at all the methods that always end up on top 10. So it doesn't matter which one you use, which perturbation, then it's still pretty good. It turns out actually our X learner turned out to be really good, which actually for some reason my student didn't want to use it for a while. So I said, I want to see how it works. And T learner, even in the original X learner paper, we know it's a very good method. We end up with 6 kind of good models across these different perturbations. We felt it's kind of arbitrary choice because many different researchers might end up doing different choices. And then we aggregate them into an ensemble CATE estimate. And then we did another combinatorial search for interpretability. We only want to use, we want the subgroups only depends at most 3 of the 16 binary features and see whether we can still see the signal. So in a nutshell, we end up using the PCS framework as the guidelines, but a lot of details need to be worked out, right? So conceptually it's articulated in the framework, but in practice, calibration was introduced. T-statistics had to decide. This ranking has to be made. So a lot of details had to be worked with the context in mind. And then we also did interpretability added. So we end up finding 6 groups. So for the GI event, we find that if you have a history of GI event before, Vioxx really have disproportionately reduced GI risk compared with naproxen. And if you have history of hypertension and prior use of steroids, also have reduced risk. or old age, you prior use of steroids. For the cardiovascular events on the right, if you have history of atherosclerosis, this is basically you already have plaque. It's really bad. It's very worse. You definitely don't want to use it because you already have problem, have these deposits, and Vioxx seem to be also causing some blood clotting, and just to make things worse. Or you have usage of aspirin. You use aspirin, probably you already had a problem. That's why you want to thin the blood. Therefore, don't use it. And the last group is kind of have a little poor generalization because we don't have any event. This is a compared with test data. Then we submitted the paper because there was a paper deadline for that special issue. And meanwhile, we want to do some external study. And there's another study called Approve. They just some quotes from a paper from 2005 saying that even you have clinical trials, conclusion from one study may not be applicable for another because the drug is not going to be used only for people arthritis, right? That's the patient who was recruited to the first study. And there's difference in populations and clinical monitoring, so it's always good to have a replicate in the sense that for another study. The Proof study was also done by Mark with fewer people. The treatment arm is the same, control arm is placebo. So they're not directly comparable, but you can still use it to give evidence for validity. And the study goal was also different. They were looking at people with certain kind of polyps and see whether Vioxx will help because it's anti-inflammatory. But this study was terminated 2 months earlier because the toxicity of the Vioxx drug. To summarize, 4 after the 6 groups were kind of supported. By the new study, we have to do some mapping, but interpretability really helped because they're not exactly comparable, but we made the argument these groups still make sense, have disproportionate increased risk for patients with prehistory GIO. So these groups are still special, but it's increased because the placebo is compared to. You see, so it's not direct. Before it was reduced compared with naproxen, but now with placebo, because both increase the risk. So the conclusion is a little different, but this is still special groups seem to be sensitive to this Vioxx. And then the other interpretation is the same. Still disproportionate increase even relative to placebo. All 3 groups seem to be holding up. And the 2 groups without a check, which is too small, we couldn't have one way or the other evidence. I mean, one conjecture is that the Vioxx in terms of GI event is worse than naproxen, and it's better than naproxen, but still worse than placebo. Basically, don't take the drug. It's still it's NSAID, cause stomach problems. So to summarize, the framework Veridical Data Science or PCS has looked at the whole data science as a whole life cycle. And we have 3 principles and documentation to go with it. And we really aim for responsibility, reliability, reproducibility, and transparency. And the PCS is a general framework, as I demonstrated. We can go beyond supervised learning to causal inference. And it was really good that we had the validity result from another trial, which is different, completely independent, different patients. And I cannot emphasize enough the importance of domain knowledge to have both Kevin and David also quite knowledgeable because he had looked at the data, especially Kevin as a physician, when we interpret result and to see something sensible. We just don't have the power just based on statistics and machine learning to really have 100% assured conclusion. So we should always bring in domain knowledge in the modeling stage and also in the validation in the whole process. But keep the test set aside. So we don't talk to the, look at test set and talk to the expert. So everything's kosher in terms of checking on the test data and the external study. So PCS is also the way we're working, using it really as framework also to generate hypotheses. So causality is something I got interested in the last 5-6 years, that I think we should really think about causality as a whole evidence spectrum instead of yes or no. We often don't have the power to decide yes or no, but we can collect evidence. And like the COVID pandemic, which my group had worked on, Jeff mentioned my Georgia Tech talk was actually on COVID. We do county level prediction. There I thought a lot, how we're gonna help decision makers. Decision had to be made. Sometimes you don't have enough evidence. So there's an operational definition of causality is you want evidence to act. And then you have a whole range of evidence to help you to make a decision. I mean, in COVID, without any decision as well, right? Because we're not preventing any spread. So you have a whole spectrum from the physics laws to the FDA, I would call average effect. And now precision medicine try to go to the next level instead of individually, but at least subgroup level. And predictability follows from causality. Stability also follows from causality. So I think putting together, of course, computability is always there. We can do hypothesis generation. And we have done at least 3 projects in biology and neuroscience. So we use this principle to design, to do, the first one is really select a number of components in non-negative matrix factorization from gene expression spatial data. And then we actually did follow-up experiments, use local correlation network. The prediction didn't hold, but we did find a lethal gene. We still try to figure out why it kills the embryo. That was for Drosophila. So we basically, that was our evidence to get the labs to do experiments. I'm much more humbled now that I want a lot more evidence than we went in the 2016 paper before I put anybody into wet lab experiment. The next one we did a nonlinear, added stability to random forest, and also to suggest a Boolean interaction between biomolecules. And we were going to do some experiment with biologist Sue Seneca, but the pandemic stopped that. So we're now adding a track based on iterative random forest in the UCSC genomic browser. So people can use our results to maybe designate their own experiments in different labs. And the deep tune is really a deep learning work using stability and predictability to understand V4 neurons and finding something we call deep tune images that excite a particular neuron for a very, very difficult area called V4 in primate visual cortex. I like to think, I know some of you really work on experiment design, so this is really thinking aloud at the end of talk, knowing the audience. I think Jeff is gone, too bad. Otherwise, I'll be interested in hearing what he says. I think PCS can be used as general experiment design principles. You basically, when you fit response surfaces, you have multiple ways. So you use the prediction to select the different surfaces which fit the data almost equally well. And you might even consider multiple metrics. So this is all P and S. And suppose you have 5 response surfaces. Then they pass the screening and you integrate it, either maybe take an average, you take the worst case, depends on the context, right? Sometimes you want to be the most conservative. Sometimes the average is good enough. So you aggregate in some way, and then maybe use even perturbation interval to decide where you set the next batch of experiments and set the parameters. And I think a possible important application is actually computer simulation design, that you definitely use different response surface technologies that you do have the problem too, that you have multiple surfaces. So I hope some of you find this interesting. Not just for experiment design, but in general, supervised learning. There's still a lot of work to be done for a particular problem, as I showed you in the Vioxx analysis. The principle is there, but I'm not trying to say that you do this and that. Give you the principles and the concepts, and then you bring in domain knowledge and documentation to help to go to the next step to make specific choices about what perturbations and. But the framework tells you these are the things you should consider. And we have many, now I have 7 projects from my group using this principle. 4 motivating examples, projects, which before the paper came out, and 3 after. And I'm much more encouraged than when the paper came out. Of course, people are always at the heart of everything. So I'd like to thank my group who really very, very supportive. We often take, our paper often takes 3 or 4 years to write. And I had a very good experience getting 12 of my members to jump on this COVID. Then we took 2 months to write a paper because we want to document the web, what we did at the website called covidseverity.com. If you want to take, we have a lot of good visualization and also data prediction. And there called covidseverity.com. I thought the website should be obsolete by this point, but the search is happening, so it's still useful. We really aim at solving problems with everything we can find: critical thinking, algorithm, good communication, and we're now also doing theory, both on random forest and deep learning, after we have good experience with both. And I'd like to thank, we also need funding, NSF, ARO, ONR, and Chang Zuckerberg BioHub. I'm also working on a book with my former student, current postdoc, Barter, and we have an MIT Press contract. Hopefully we deliver early next year with a free online copy, and also the paper copy maybe arrive end of the year. And it's using these principles and really talk about the whole data science process, about common sense, about making connection from symbols to reality, and good habits, documentation. We have some math, but not a lot. There are a lot of good books on math, so we thought we could do minimum to just get people the ideas. So hopefully you find it useful. This is for upper division and graduate, beginning graduate courses. Or as a supplement, then the more mathematical driven ones. I want to have a shout out for what's going on in Berkeley on data science. We now have Associate Provost Jennifer Chase leading our new division called Computing Data Science Society, and Statistics Department is in the process of moving into that division. We used to belong to physical and mathematical science. We still belong there, but we're in the process of moving into the new division. And we have really fantastic data science education program. I had the fortune to work with colleagues to design Data 100, and Data 8 was the first one. There's not free, $500 you can get online, take the class online with DataX. And the vision was in a report. I was on the committee called the FAB report to 26, both on educational and organizational vision of data science. Thank you.
Okay.
Questions?
Thank you very much. We open the floor for questions and discussions.
Hi, Ben. Thanks for the wonderful talk.
Thank you.
So Merck had no idea that there would be gastrointestinal issues with this oral medication.
I only had minimum reading on that. I think I should not comment on that. Probably there are a lot of reports. I haven't done a thorough study. I think there was definitely a report of, yeah, you should read. I think
Okay.
to find out exactly what happened.
Right.
I just haven't done enough investigation to know how much they know, how much they don't, to say anything.
Mm-hmm.
It's very expensive. I think it's usually a very expensive drug. And there are definitely unexpected outcome. So I think they try to block something called COX-2. That's a protein enzyme. And COX-1 is the one more related to clotting. But apparently COX-2, when you block that, also has impact on COX-1.
Okay.
So I could also see that maybe just unexpected, because they're not blocking COX-1. They try to block COX-2, but it turns out that COX-1 is also affected, seems to be. But this is just pretty educated reading.
Okay.
Yeah. So I could also see that it's unexpected, just because for a while I was confused because I was reading and I keep reading COX-1 and what's going on. And I read somebody saying that there was a post saying that even they block COX-2 and COX-1 seems to be implicated too. Because while I was reading it, I was keep thinking, did they really block COX-1 or COX-2, right? Because I know COX-1 is the one related to clotting. So I kept going back to check they block COX-2. But
you.
it was also a report that some of them researchers were also doing consulting. So there was a lot of interconnections of different people.
Thanks.
So follow the NPR. They did usually, hopefully more fair coverage.
Yeah, I'll also ask my son, who's an interventional pain specialist.
Yeah, you should ask him. Yeah, let me know what he says.
Yeah, I'll ask him this evening.
Yeah, because it was big news, right, at the time. Actually, I didn't quite know about this drug until we start working on it, right? I don't take a lot of painkillers, and but for last week I read more. It was even bigger than I thought. I read a bit on Wikipedia, but then the recent rating made me feel like it was a really big deal. Like $5 billion was paid.
Is this also an opioid or no?
No, I don't think so. Yeah, I don't think so. It's blocking this. Your son probably knows better. Consult him. Yeah.
Yeah, I have a question. I think, thank you for your talk, and it was really nice talk, and the principles that you brought in, in terms of data science, and quite fascinating, I'm wondering whether you can comment about the design stage, because the analysis that you conducted are randomized studies, and they are well designed, well collected and well measured, and in the sense like gold standard. But in terms of data science, there are a lot of convenience samples that are subjected to all kinds of biases, in terms of collections, because they are conveniently available, so in that sense, in your framework, do you have any kind of a quality control checks or any kind of the assessment to expand to that area, or whether you can comment,
No, actually the original framework was designed for supervised learning, right? It was not designed for, when we first did it, was supervised learning. So it's convenience sample. So generalization is always a problem. So our approach is that with the data you have, at least you should do enough perturbation to make sure within the data you have tried the best you can. So that's why you want to do different versions of data perturbation. And if you don't do random split, you actually do like meaningful split. Like if you have data collected before 2000, you take that as a training and the one after 2000 as a test. So all of that was the original PCS framework. This one's new work to generalize to causal inference. Actually.
Yeah, but at the same time, it is the domain of knowledge too, right?
Yeah.
I mean, in the sense that if you know that it's not a random sample, possibly nothing you could overcome it, right?
No, I disagree. You can still do something. You might not be able to generalize well, but often you do have the convenience sample. That's why you want to document and saying, I mean, my first inkling of doing this perturbation was that my collaborator, Galan student, collected video data for 2 hours. I was like, what if the student made a decision, only did 1 hour, 15 minutes? Would I get the same result? That was basically my first inkling to go down this path. So I want to make sure that whatever we discover won't be changed because if I shrink the data by 10 less minutes.
Yeah, so in that case, you have to have resources, right? I mean, you have to have like the data sets that you can do all that kind of stuff, right? I mean,
no, but you can always do perturbation to the data. You can add some noise to the data. Leo Breiman likes to do that. So there are things you can do. I agree that if it's not a random sample, you're limited. But most of the time, we don't have a random sample. And science has progressed not always because we have random sample. So this PCS, that you do the best you can kind of approach and document it.
Yeah, I mean, it is true. It's not a random sample. I mean, real world possibly you can't get random sample, but at the same time, unobserved confounding is there, right? I mean, it is.
You are really talking about observational study for causal inference.
Exactly. Yeah.
So that's something I'll be very interested in looking at, but I don't think I have anything to propose right now. But I do think stability does help because in our design of experiment, that's what I say. If you have predictability, I think you add some data perturbation, you counter a little bit some confounding, which I need to work harder to articulate. That's my hunch. It's not the same as randomized trials, but even randomized trial, you have a problem. Might have many features. You don't have balanced sample either.
No, I mean,
So I don't see always the randomized trials always the gold standard. I think some observational studies can be more informative with the domain knowledge.
yeah, but the only thing is that when they do randomized studies, at least they make sure that they measure things more correctly, you know. I mean, that's
But whatever you
planning. Yeah, planning in terms of, you know.
But when you end up with, that's why people do re-randomization, right? Things are still not balanced. People have to do some post-processing. I just think that there's nothing's always better. The context matters a lot, as you said, domain knowledge matters a lot.
Yeah.
Documentation will help you to share the domain knowledge with the user. There's no magic, but we have been very, I feel like, successful using adding stability to predictability and domain knowledge.
Thank you. It's really nice talk.
Thank you for the questions. Other questions? So the paper, if you go to my website, a lot of the papers, high-level papers are on the front page. And there's also a recording of my Bryman lecture at NERSC last year. Was the first part very related. The second part was using neuroscience, deep learning example, not the more recent clinical trial example. I hope you guys will, join us and develop further, or say this works, that doesn't work, right? The idea, I think, is very common sense. It's just now everything we do, we actually report it. Then we clean the data somehow, and we put a probability model as if nobody has touched the data. And most people who work on data will tell you that 80% of our time spent on cleaning the data. I don't think we can afford to only work with clean data. We need to get in there, get the raw data, and do the processing with people, with the domain knowledge. I think the time is over. We only wait for clean data. And the clean, actually, we don't know whether it's clean or not if you don't know how it's being processed. So it's an illusion. We try to turn our head away not to look at it, and live in our beautiful world of probability models. I tried to open that up. I said, no, it's useful, but it's not that beautiful, but it's okay.
Well, I think there's been more than one instance where a clean data set missed some of the more important information. So it's, you end up removing outliers, and it's the outliers that were of interest.
Exactly. So we should really go to the instrument, right? Understand how the instrument work, or how, it's part of statistics. And the pre-processing, we have to increase it. And if you do that, you have the problem of who clean the data. You have two graduate students, they probably don't do the judgment call the same way. And at least we should run the pipeline, with two different ways of cleaning data, and hopefully more or less they agree, right? And also Bayesian and non-Bayesian work on the problem. Will we get the same conclusion? If we don't, we need to find a way to consolidate that, because reality shouldn't depend on whether we have Bayesian glass or non-Bayesian glass. These are just in common sense questions. I think we need to face it.
I think your framework's actually a good way of working with even simpler problems as well, for that matter. I mean, just a matter of being careful in how we work with data. Yeah,
it's really, it's just honesty and common sense. It's not rocket science. Maybe it's not rocket science in that sense. You've been careful.
You teach this to undergrads?
A bit. I did a machine learning class, so I did a bit of that. And the PhD level class, that's what I teach. And a lot of this framework also had a lot to do with my teaching, because I always felt a little sheepish about, where the random variable comes from.
Yes.
And I decided finally to address it.
That sounds like something that might be in Stat 101.
That'd be great. I mean, we'll have a textbook on the internet next year, so hopefully feel free to use any parts and anything. But that's what I hope be a resource too, for people to take parts of it and whatever. The book starts from problem formulation, data cleaning, computing platform choice. And I make a big deal about when you introduce random variables, what it means and what are the standard cases. I don't introduce random variable until halfway through the semester because I want to do it very, very carefully. Not everything you have data is a random variable. You're making assumptions. Random variable, you're assuming that there's another situation, you have another realization of the same random variable, and you're tying them together. And that's a stability assumption. It took me 25 years to realize that, but never too late, I suppose. Using a random variable, you're making assumptions, which didn't occur to me. I always wrote big X in my first class for decades, because that's how I was taught. And but when you try to, it was helpful to go. I really spent a lot of time in machine learning and also into causal inference. I think both were really helpful to getting myself out of my comfort zone. Hope you guys take a look, and even you decide don't like it, let me know how. That'll be really useful for me too.
Well, one advantage of this doing it by Zoom here like this is I can put in certain stuff on my internet browser while we're doing it. So I've already done a couple of those here during your talk. So thank you for a nice talk.
Well, thank you for the questions. It's always more interesting when people ask questions. I actually gave this talk for like 3 or 4 years now, and the whole paper was evolved in front of the whole community because a lot of questions from the audience were really helpful and became a lot more thorough and connected and synthesized than when I first started. I think the first time I gave a talk was 2007 in IMA. I called 3 Principles of Data Science. That's the first time. And it was helpful to actually give talks without writing the paper. And now the paper is written, but still we can still change things if something doesn't work. Yeah.
Okay, thank you very much. Thanks everyone for attending, and let us acknowledge our distinguished speaker. Thank you.
Thank you for having me.
Yeah, thank you.
Thank you everyone for staying
Yeah.
and all the questions.